So one of the big challenges for us in the project we did at Otis was to understand the way components would behave when they were connected in a relatively unique configuration. You can have emergent behaviors that can really be problematic, especially if it's on a military installation where having the system up and operational is particularly important because the people who are utilizing that electrical service are very sensitive to interruptions. What the Hill has allowed us to do is be able to preempt these emergent behaviors and predict them before we would actually encounter them in the field. It's been really advantageous to be able to simulate those system integration issues with high fidelity. In our prior projects, our lead software engineer would sit in an inverter room until midnight trying to get interfaces to work. And now, because of the C-Hill, we're able to get that all done preemptively up front. Usually to run through our full test plan within the Hill environment, we can do it within a few days. The controls and how they would behave were more important than the actual powered devices themselves. And that was the reason why we thought the C-Hill methodology was more appropriate for us. The logistics and convenience associated with being able to simulate large-scale systems versus doing that all in power hardware, which takes really specialized facilities that not many people have access to. The controls that we've done is a supervisory level microgrid controller, which is primarily concerned with dispatching various generation elements. We're integrating a lot of commercially available equipment, which is not inherently very secure. So for these military applications, we need to be able to add an additional level of security to pass muster. And our control system, putting together all of the interfaces between the simulation and the physical controls is time consuming, and that's something that Typhoon has largely done, making sure that we had the simulation configured in the way we needed it configured in order to run the test cases. What we've been doing for our microgrid control testing has been based off of the IEEE 2030.8 standard. If you have a system that you can say has been tested in accordance with standards requirements, that provides a sufficient level of test coverage. We've seen instances in which you might have detection and control settings that are acceptable for grid-tied operation, where during islanded operation you have transients that occur that could cause protective relays to trip. We've also seen instances in which sequencing of the way that you control various generation elements within the system, where if you don't sequence those operations properly, dynamics arise that will trip parts of the system offline. And it's powerful because you can change what you're doing and you can explore other potential possibilities quickly and easily. And it builds confidence in your customer. It allows you to de-risk your technology. It allows you to better plan and execute your projects. As more and more things are electrified, you're going to see more and more instances where you really need to have some kind of high fidelity emulation. So we're just glad that we're already down that path in the work we're doing, and it's going to be indispensable.